examples in brief. So, okay, firstly, we're talking about epidemiological models. So we might start with what is an epidemic? So one of the definitions, the CDC definition is the occurrence of more cases of disease, injury, or other health condition than expected in a given area or among a specific group of persons or animals, depending on what you're modeling, during a particular period. They're usually cases that are linked. And so the key things about this are we're thinking about a noticeable increase, we're thinking about above expectation, we're thinking about a specific sort of geography or area, and then a given period of time. So outbreaks might be similar to this, they might be more localized. Pandemics, we've got a much more extended geographical range. So it's just some of those definitions. Common feature of these, and what we're going to be looking at, because we're thinking about infectious diseases, is transmission between hosts. So one individual or one person becoming infected because the disease or the infection was transmitted to them. In this case, that infected person or case may also be a risk factor. If one person is infected, they've got a risk of infecting others. And we might have people who are a source of infection, but it might not have been recognized as a case. They might not have been reported as such. So a couple of other things that we'll include in these models or start thinking about are people can become immune. Obviously, this is disease specific, or if you're thinking about other kind of species, maybe this is not the case. With these sorts of dynamic models, control measures can have direct and indirect benefits. So again, if you're thinking about modeling the impact of vaccination, having both the direct and indirect benefit from vaccination might be important to capture. And also, when we're thinking about control measures, there might be a time-sensitive element to them. It might be key to vaccinate people at a certain age or at a certain point in the season before transmission begins. So hopefully, given this course, it's not too much to motivate why we might think about modeling epidemics. So we can use models of this format to give us an idea of the current conditions. So given that we've got a certain number of cases reported, how many infections does that translate to? We can think about predicting or projecting the future progress of an epidemic. Are we expecting it to decline, or are we going to get some growth? We might be interested in understanding some of the mechanisms driving transmission, and we can sort of try them out in our model. And then finally, we might be looking at what interventions can we use and how can we use them effectively to limit an epidemic. So we've got a few examples. So we might be interested in how many people currently have a disease or are infected with a certain virus or bacteria. So this study was looking at the burden of yellow fever. This was back in 2014. There have been updates since then. Again, we might be thinking about what we might expect to see in the future. Are we thinking that the epidemic might decline? Are we going to see another peak to our outbreak or epidemic? And what's the uncertainty on that? Maybe we're interested in looking at how this might be affected by some of the interventions that we're thinking about including. So we can think about future projections or predictions. We can also think about the mechanisms behind the transmission. So in this case, we've got an infographic talking about ways to limit diarrhea and vomiting outbreaks. So just giving some mechanisms of the transmission. And maybe that's going to affect the interventions that we think about using. And then finally, we can use models like this to project the potential benefit of an intervention. So here we've got two situations. We've got the blue showing a vaccine scenario for koalas. And we've got red where we've got no intervention. So this is the number of koalas declining without any intervention, with some uncertainty. So we've got some examples of why we might try to model epidemics, trying to get some understanding of the current state, the future state, or maybe some of the mechanisms behind it. The steps that we go through is very similar to the steps that we were talking about earlier when we're developing a model. So we think about, okay, we've got a question, we might want to identify the key biological processes. We don't necessarily have to know them all. We're going to extract them and put them into a mathematical model, again focusing on our question or our context of interest. And then once we've got a mathematical model, we can start exploring its behavior. So looking at changing the parameters, maybe estimating it from data, and looking at the dynamics of our model. Okay. So compartmental modeling is where we make another simplification. You're going to hear about a lot of simplifications. So here is a potential timeline of an infection, so for one person. So they start susceptible, and then at some point there is some transmission event, and they start becoming infected. So this is continuous. We've got a latent period where the infection is developing, and then at some point they then become infectious. So we know this is a continuous process, but we can go a long way by thinking about, okay, what are the key parts of this continuous process that we really want to explore? Again, can we simplify it to try and get some insight out of it? So we might most be interested in the time before them getting infectious, so that we would define as being susceptible to infection, and the time when they're infected or infectious. So we know it's a continuous process, but we might be wanting to break it into these two key areas because those are what we're interested in for our question. So we turn this into a couple of compartments. So here we've got a susceptible group, they're in this first stage, and we've got an infected stage as well. And at some point we've got a transition between being susceptible and being infected. Okay. So we've simplified this down into two compartments. We'd call this an SI model. So at the moment we don't have any R stage, there's no recovered stage. So if we had a whole population, we've got essentially two compartments that any one person can be in, but they can only be in one at a time. So people are either susceptible or infected, and we might consider how that population interacts. So here at the beginning, we're just going to assume that it's a well-mixed population. There's a chance that you might bump into everyone else, and all the members of the population are in contact. We'll come back to that assumption in the next lecture and how to adapt it. But for the moment, let's say that we've got a population and they're well mixed. Everyone's bumping into each other. So we've got our SI model, our susceptible and infected compartments. But we know that there's a transition between going from susceptible to infected. That's where we've got our transmission event happening. So what is that? So this kind of arrow represents the rate at which a susceptible person gets infected. And this can depend on a number of things. So because we're looking at a dynamic model, it might be dependent on the number or proportion of infected people or animals, because each infected person has the risk of infecting someone else. So the number of them is quite important. We might also have this transmission rate, beta. This kind of rate captures a lot of things. It captures the chance that someone comes into contact with an infected person, and It also captures things like, if you meet an infected person, what is the chance that you will become infected? It might not be 100%. So this can capture a few different processes. Okay.
What was the difference between the two things?
Okay. That will make more sense when I come back to different contact structures. So if it's all right, I might return to your question a bit later. Okay. So let's say you start with your population, nobody's infected, and if we've got no infections in the population, the risk of becoming infected is going to be 0. Exactly. We're going to talk about frequency-dependent transmission. That's most appropriate for models in humans. Livestock models get exciting because you can look at things like density-dependent transmission. I'm going to...
Katie, can you give me an example of a livestock model which needs density-dependent transmission?
Not off the cuff. It's a really weird one to conceptualize.
There arguably isn't one, but there is a dogma. If you read some old papers, they'll say frequency-dependent transmission is for humans, and density-dependent transmission is useful for wildlife. Okay? Because they were thinking in old ecological ways about populations which either grow at constant density or grow at constant size. There are some cases where transmission rates seem to be bigger the larger the population size. So my day job, bovine tuberculosis, you do tend to see more positive animals in bigger herds. That's probably because how they're managed and how they're contacting each other rather than just the size. These terms are really misleading because when people say density dependent, they normally mean population size dependent, and they aren't thinking of density at all. And a lot of times when people choose density dependence, it's as a crutch because the model doesn't make any sense. Okay, some really bad examples, which if anyone wants me to say bad things about Roy Anderson and Bob May, we can over coffee, not in a lecture, with rabies models, which they use density dependent transmission just because it was a good fix. They actually have bad implications for what you would choose to do for control. For every population where we have empirical evidence, transmission seems to be frequency dependent, and that seems to be the most sensible starting point. And when it looks different, it's normally because we've missed something, like age clustering or spatial clustering. Even worse, there's no consistency with how people use these terms in the literature. We're getting better, but there's horrible terms like pseudo-mass action, true mass action. Nobody agreed on what any of these made. And even worse, sometimes mathematicians especially will just divide their population by the population size, so it's a population size of 1, and then they look exactly the same. Okay, so be wary, rant over, and we will only live in a frequency-dependent world.
Yes.
Sorry? So what's the link between, when we are having a frequency-dependent transmission and density-dependent transmission, the beta we are defining. So is it the same thing irrespective of the type of transmission we are working with?
So if you have a fixed population size, it amounts to just changing the units of beta. So density dependent, your infection term is beta SI. So it's the numbers of infectives which are important. For frequency dependent, it's beta SI divided by the population size. So it's the proportion infected, which if you think of a well-mixed population, that's sort of what makes sense.
Yeah.
That's what makes sense. But at a constant population size, it just amounts to changing beta to beta over n. If your population's growing, it gets a bit more exotic. but again, you're probably modelling something different other than the thing you think you're modelling.
Because now that you're bringing time to think, like in our setups, like when we have outbreaks like the value of river that affects both the animals and the humans, and sometimes it happens in arid areas where the population moves on the move, and sometimes cannot tell the actual population at some point, yeah, even the animals. I'm just thinking now that it's
So,
Yeah.
if you think it, so that essentially that's a spatial modelling problem because your population's moving, and again it's modelling the spatial structure and the movement of people across the map is the right way to handle that problem rather than using density terms as a proxy. Yeah, because you can mathematically you could use density terms to get around that and describe it, but it could have the wrong implication for your control measures. So the classic one, the classic example for this is rabies. So rabies control has historically been assumed to be density dependent due to two people that I'm not going to mention the names again. And as a consequence, culling has been the preferred option, culling the dogs to reduce risk rather than vaccination. And in fact, when you look at transmission, it's frequency dependent, but it's very spatially dispersed. So if you model the spatial structure, vaccination's clearly the better intervention than culling. But you wouldn't see that from a simple model that ignores space. So a density-dependent transmission term can be used to approximate the fact you're ignoring space, but actually that may lead you down the wrong path for what control intervention you should be using.
A little bit complex.
It is complex, yeah. And actually, for something like RIF, where you've got two hosts and you've got, you don't have a well-defined population, it's the sort of thing an individual-based model is almost a better description than assuming things are well mixed, because they absolutely aren't, and that's an important part of the dynamics.
We are going to get onto structured populations.
Yeah.
But for the moment, we're going to keep going back to that well-mixed assumption. Before jumping into, well, the next thing, but going back to that geographic separation, there's lots of stages you can go through with your modelling before you go from, okay, we're going to assume everything's well-mixed and smooth it all out, to we're going to model by pixel. There's steps you can go through. So it's splitting into different populations that are linked, and then you can go more and more granular depending on your problem. So, but we will come back to that. All right, we're going to focus on frequency-dependent transmission. So here we're thinking about if you are interested in the risk of a susceptible person becoming infected, we need to capture that there's a proportion of our population that are infected. So here it's, that should be a 7. Typo there. So here we've got a proportion of people who are infected, because each infected person is themselves a risk factor to others. And then we might have something that captures the probability of infection given contact. So here we might say an effective contact if we're combining the two. And that's the idea that if you bump into someone for like 5 seconds, your chance of becoming infected by them might be different to if you give them a hug, something like that. Okay, so what does this look like in terms of equations? So we're thinking that everyone in our population at the moment is either, sorry, go on. Yeah?
4 beta over 6. So are we not considering the number of susceptible people?
So the number of susceptible people is considered in that it's part of the total population size, which should be 7. Let's ignore that. Yeah. 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 So they're captured in the total population size. We're not necessarily capturing them explicitly, but this is our term that we're interested in. So what we were just looking at was beta, That's our constant, our parameter. Then we've got I over n, so our total population size. So n is s plus I. And this term is kind of acting on or affecting susceptible people. So when we consider the infection itself, it depends on our parameter beta. It depends on the total population size, because we're thinking about frequency-dependent transmission. And it depends on susceptible and infected people coming into contact. So we've got these two included. Okay. So we can start writing our equations for this model. Everyone in N, the total population, is either susceptible or infected. We're not thinking about births and deaths or anything else at the moment. We're just focusing on S and I for now. So we've got a pair of coupled differential equations. We can start looking at what that looks like in terms of a graph. So here, if we look at the green, that's our susceptible population. If we start with almost everyone susceptible and maybe one infected individual, and then we simulate that forward, this is saying that if we've got a lot of S and just one infected person, we're going to get slowly a growth in the number of infected people as people move from S to the I compartment. That's going to start slow because it's going to depend on our population size, ramp up as we've got lots of infected, and then start petering off. We're going to get a slowing gradient as we're running out of susceptible people to infect. Okay. But the place we end up is everyone's infected in this model. And because we don't have births or deaths, that's pretty much where we stay. Yes. So beta here is a constant. Okay. So it's a simple model. It might be enough to describe the problem that you're interested in. We'll come back to some of the assumptions in terms of this parameter beta. Here, we've done that mathematician thing of dividing through by n, or saying that the population size is 1 just for convenience. You can do all of this exactly the same with n. We can go through it if you want to. But here, just to keep things tidy, we're going to say that the population size is 1, and we're thinking about proportions instead. So with this, we can start in this very simple model to solve these differential equations, or think about what the equilibrium might be that we've already started looking at. Okay, so everyone in our population, in our total population n, is either susceptible or infected. If we've got a population size of 1, that means S is equal to 1 minus I, because people are either infected or susceptible. If we've got this differential equation, we've got this value for S, we can substitute it in, and then start rearranging so that we can do things like separation of variables for solving this differential equation. So I mentioned that for differential equation, there's a whole bunch of different methods. Separation of variables is one. Essentially, we're taking all of the I terms onto one side and all of the T terms onto the other. So we had a previous example on this as well. And this means that we can start to integrate. So separation of variables works because essentially we're reversing chain rule, if you think back to our differentiation lecture. So over on the left-hand side, we're integrating with respect to I. Left if you look this way. And on this side, we're integrating with respect to T. Okay. So integrating the right-hand side is easy. We've just got a constant, so it's beta t. We would have a constant of integration. We can come back to that later. Left-hand side is a bit trickier. We have to use this technique called partial fractions. This is just another method for making integration a bit more straightforward. Essentially, we take what we've got over on the left-hand side and we turn it into more convenient fractions to work with. We split this up. now we've got two integrals added together, so we can treat them separately and integrate both of these to get log base e of 1 minus I plus log base e of I, which we can combine with some log rules. Okay. So, and just a note, the ln is log base e. Ooh, computer screen's gone weird. Right. So, we put that together, we've integrated both sides, we've used separation of variables, we've got lists. This is not very nice to work with. Ideally, we'd want I as a function of t. So we know we want to make sure that the natural log or the log is on its own, and then we can take the exponential. So we do that. So now we've got I over 1 minus I is equal to e to the beta t. And we can do a bit more rearranging to get I of t on its own. So we've got our coupled differential equations. Because we're assuming everyone in the population is either susceptible or infected, we can essentially solve one of those equations. And once we've done some integration, some rearranging, we get an equation for I as a function of t. So what does that look like? Well, if we think about the fraction of people who are infectious, assuming that we're not starting at 0, then even with one infected individual, there's a risk of infection to susceptible people. That's going to start slow, build up as we've got lots more infected people, and then the gradient of that is going to get slower and slower as we run out of susceptible people to infect. Okay. So another familiar kind of form of this solution. Okay. Once we get to this point, that's pretty much where we stay. We've already infected all of the susceptible people. There's no one coming in, so we've run out of people to infect, and that's where we stay. Yeah?
So if they did recover, it will go down?
Yes. So we might have, so before I move on, so this model might be enough to describe the problem over the time period that you're interested in. However, we might have recovery or something where someone becomes infected, they move from susceptible to infected, but then they might move back to being susceptible. So now we've got something that's increasing the size of the susceptible population again. So we could add an extra term here. So we've got a recovery rate gamma. We're going to say that our new equation for the susceptible population is this infection term. Here, n equals 1, convenience. And then we've got this recovery term. So people can get infected, they stay infected a while, and then they move back to being susceptible. Okay. So this just adds an extra bit of complexity. We can do the same thing in terms of solving this system. We can use the fact that everyone in the population is either susceptible or infected to rearrange our equation for di by dt. Sorry, go on.
Yeah, what up there is, so up there is beta I over n.
Yep.
But in the equation is beta n c I.
Yes, that's because we've made n equals 1.
No, that's not what he's saying.
Oh, okay.
I think he's talking about the minus beta si.
Yeah.
So beta I over n, like he's not seeing the s. That's what he's asking that.
Ah, I see. Okay. So both of these kind of rates, these terms, are acting on one of these populations. So beta I over n is affecting the susceptible population. That's how we move along this arrow. And then we've got this recovery rate gamma, that's acting on our infected population. So that's why we've got a gamma I. And that's why the S, because these are acting on either the susceptible population for the transmission term or the infected population for the recovery term. Okay.
An example with disease with an SIS.
Example of disease of SIS. where there's no immunity. You go on.
Or you can give it.
No, go for it if you've got an example.
Measles.
Malaria.
Measles, right?
So
Yeah, you recover and then you go back to infected.
So measles is perfect
Yeah.
immunity. You never get it again.
So that would be an SIR.
Once you're dead, yeah, and you're replaced by a child who is susceptible, an SIS model might be a decent approximation for long-term dynamics of measles. Yeah.
But the proportion will die.
But you'd be missing a lot of the biology there. You'd have good parameters would be quite crazy.
Yeah.
Because the key thing is all of those who are infected with measles are not infectious in that model, in an SIS. You need an extra compartment just to account for the fact that you're only infectious for a very short time.
So some of the examples,
Would be a good example.
there's one. For the SI model, a good example of that is if you're thinking about infection in a mosquito. So they're susceptible and then they become infected and they probably die at that point.
Yeah, but the reason why I thought malaria wasn't a good example is because you're not infectious to others. I mean, unless a mosquito comes and just bites you and bites someone, but you're not really posing threat to others directly. Gonorrhea is because you are infected, then each contact you have with someone else makes you infectious to them.
Yes.
Yeah, cholera as well, yeah.
There is some immunity for cholera though. So for cholera, yeah, if we were comparing, we've got our SI model, we've got SIS, and then we're coming on to SIR. And in R, we're assuming that you've got some recovered period where you might be immune. And that might be a better approximation of some of the things that came up. If you've got a disease or something going on where there is no stage where you're immune, this is a good fit for it. Okay. So, what does it look like in comparison to the SI model? So here, we eventually end up that everyone's infected, that's where they stay. But for the SIS model, we might have something that we call endemic equilibrium. So this is an equilibrium where we've got both susceptible and infected people in the population at the same time. This means that we're topping up or replenishing the susceptible population just enough to keep infections happening in the population. We cannot get to this point with an SI model. We do need that kind of replenishment of susceptible individuals. So we started putting together our equations. We've got an SIS or an SI model so far. We've included some rates, some parameters in our model, like gamma. We might be interested in, well, okay, how do we get to putting a value of gamma in our model? What does it actually mean? So here we're thinking about our infected individuals and how they change over time if we ignore the infection process. So here we're saying, okay, we've got people in the infected class. How long are they going to stay there? What's their average time being infected? Because we've got this term, this is like a constant risk of recovery at each time step. And we can solve this. So we've got essentially an equation of exponential decay. If we start with 100 people in the infected class, over time, that number is going to decay according to this equation. We've solved this previously, and we can describe it as I of t is exponential to the minus gamma t. So if we start with 100 people, over time, that number is going to decline. If you are trying to parameterize your model, you might be interested in where do I get gamma from? How do I start if I'm reading literature? where should gamma come from if I'm not estimating it directly. Well, one of the things that you can consider is what's the average length of time that people are infected for. This is something that you could potentially get from the literature. Some studies might follow people through their infectious period. And you can use this to give you sort of a value of the average length of time infected, and that would correspond to 1 over gamma. That's because we've got an exponential function here. So if we think about the average of this function, if we look along the entire infinite kind of decline of the number of infected people, the expected value of this is 1 over gamma. And separately, we can come from where that comes from. But this is quite useful. So again, studies where you might follow someone through their infectious period and then measure how long they were infectious for, we can do something like that. We can observe that, which can give us an idea of the average length of time that they're infected, and inversely, the recovery rate. Okay. This is a bit weird. Already, you can see that initially, the proportion of people who are infected declines very fast. And then we might have a few people who are infected for a really long time. So the way we set our equations up has made an assumption, an implicit assumption about what this shape looks like. And we're going to come back to that assumption in the next lecture and how we might change it and whether we want to worry about it or not. Okay. We can do the same sort of thinking for the force of infection. So this risk that a susceptible person becomes infected. So back in our equations, we had our beta. We care about the proportion of people who are infected in the population. And we can define this whole term as the force of infection. And usually this is denoted with a lambda. You might see it with other things. So this is the risk that a susceptible person becomes infected. It depends on the parameter beta and the proportion of the population that's infected. Okay, so if we only wanted to think about our susceptible group, so if we had 100 people starting susceptible, we might like to ask the question, on average, how long are they going to stay susceptible before? How long before they get infected in their life? So we can start getting at this by thinking, well, slightly rephrasing and saying, okay, what's the average age at which people become infected? We know they've got a risk of infection. We've defined a force of infection. So we've got a constant risk that someone might become infected. Again, we can go through the same steps that we just did. If we just think about our susceptible class, and we only think about how they exit it through infection, we've got an exponential decay differential equation. We can solve this. We can look at the expected value of our exponential function, and we can get to this. This A is the average age at which people get infected, 1 over lambda.
How do you differentiate between the transmission rate and the force of infection?
Yes, is a really good question, because beta, yeah, but if you look at the literature, people define things in different ways. So often you'll see beta used as a parameter to give us an idea of a transmission rate. There might be more than one thing going into this. There might be more than one piece of information going into this. So, for example, we might have the type of contact between two people, and given a contact, what's the actual probability that someone becomes infected given they're exposed to a virus, a bacteria. So here, force of infection is a standard term. Transmission rate can, depending on the study that you're looking at, might have slightly different definitions and what that beta is capturing, basically. You might also have models where the force of infection is affected by other populations, and we'll come back to those as well. So, yes. Okay, so here we're thinking about our exponential decay of susceptible people, given that they're going to get infected. And we can ask the question, how long before they get infected? What's the average age of infection? It's a little bit odd because this depends on I. But we can think about this at the beginning or a particular stage of an outbreak. Okay. Yeah.
So in other words, the transmission rate is also, or at least the way I think of it, is dependent also on the pathogen, right?
Yes.
And whether it's, airborne, whether it's airborne or spread by droplets or contact. Whilst
Yes.
the course of infection might be more to do with the number of susceptibles that are available and also the rate of contact.
So rate of contact, yes. Number of susceptibles, because the force of infection is acting on the susceptibles, that's sort of separate. So rate of contact, definitely, that would be something you'd think about in terms of the force of infection, because that's the risk that a susceptible person will experience in terms of getting infected. But yeah, you're right, it varies by pathogen. Yeah. Okay. So, oh, go on.
When you say average, is that just the previous slide?
Yep.
When you say average age at which people get infected, what are you referring to?
Yeah, so it's thinking about, okay, let's say we've got a population, and this is probably most easy to think about in terms of an endemic disease. So a disease where we've got a constant kind of number of infected in the population. We won't think about seasonality, we're just thinking about a constant number of infected people. If we've got that situation where we've got an endemic disease, a susceptible person might be going about their normal life, and this might be years before they come into contact with an infected person. It might be months, but we can use this force of infection, this risk of a susceptible person becoming infected, to give us, on average, not everyone, on average, how long before a susceptible person comes into contact with an infected person and becomes infected.
So, is the age in reference to the disease?
Great question. No, this age is for the average susceptible person. So it could be their age in years. I've got an example coming up, which might.
This is the age at first infection.
Yeah.
So if you're familiar with survival models and the idea of survival, I think that's a good way of thinking about it. So the force of infection is your risk of becoming infected in the population. The higher that force of infection, the earlier you're going to turn and become infected. Lower forces of infection means that you're just less likely to meet the disease, so you're going to have to live for longer before you get exposed to it and become positive or become infected with the disease. So a disease like measles has a very high force of infection, and that means your mean age at first of infection is very low. Okay? Whereas something like tuberculosis, which is very relatively poorly transmissible, and the force of infection in the community is much lower, and you have to live much longer before you become infected. Does that make sense?
I think so. I think when the numbers start coming in, some of it will make sense.
Yeah, we've got a.
Excuse me?
Yeah.
What are the limits to force of infection?
Oh, so let's have a think. So here we've got. Sorry? So we had a question of what are the units on the force of infection? Did you also have something on units?
Okay, can I talk? I was going to say, so how does that, in that scenario that you're just describing, how does that apply to COVID, for example? Yeah.
It doesn't. So the age of infection for the initial wave of COVID will basically be the average age of the
Right.
They'll be skewed a little by the contact rates and how they might vary by age. So this concept really comes from thinking of an endemic population where we can characterize an average course of infection.
Yeah.
Right.
Okay? For COVID, because it's a dynamic, or in the initial stage it was a dynamic
Mm.
stage, it's the patterns of exposure by age drove the mean age at first infection, yeah, which is different from this. This is thinking of a more long-term
Endemic.
endemic situation.
So we had a question on the units of the force of infection, so we might be interested in thinking about, so I is in terms of population, number of people, N is in terms of population, number of people, and beta we can think about as a rate. But we might have, as I mentioned, and we'll come back to this, a couple of things going into beta. We might have what's the infectious dose of a disease, we might be interested in that, and what's the chance of an effective contact, so capturing that infectious dose, but also thinking about the types of contact that we might have between different people.
All of those have to cancel out.
Yeah.
So the dimensions must just be a rate, 1 over time.
Yeah.
And we can do that by dimensional analysis of the equation, because ds by dt must have dimensions. People over time, susceptibles is people, so lambda has got to have dimensions 1 over time.
Cool. Okay, so we defined this contact, this idea, this average age of infection, yet mostly for endemic disease. So what does it look like? We've got proportion infectious. If we've got a high proportion of infectious people in the population, it doesn't take very long before you come across an infected person. So your average age of infection is quite low. As that proportion gets smaller, your chance of bumping into someone who's infectious gets lower, and so the average age of infection gets higher. It takes longer through your lifetime before you bump into someone who's infectious. And we can see this from the study, which was looking at the mean age of infection in different regions at a particular time of this study for measles. Found, so we've got different mean age of infections for each of these different regions. There's lots of factors that can be affecting this, but just splitting between different regions and thinking about how that might vary from population to population. This is useful to think about because if you're thinking about an intervention and, for example, you're thinking about a vaccination activity and you want to target children, this might give you an idea of when's a good age to target children, taking aside that operationally it might be easier to get to school-age children or infants. Okay. But yes, mainly focusing on endemic disease. Okay. So we've done SI models, we've done SIS models, and now we're going to come back to this and think about an extra step. So some of the diseases that we've already started talking about have a duration of time after becoming infected where you're immune or you can't become infected again. So again, we know this is a continuous process. We know you start susceptible, there's some transmission event, we might have a latent period, you become infectious after a while and then slowly become immune. But we're mostly interested in these 3 stages: the stage where you're susceptible, stage where you're infected, and then this recovered stage. Okay. So we're going to use this for our compartments. So now we've got our SIR model, our susceptible, infected, recovered model. So we've got similar things going on in terms of we've got susceptible people moving to the infected class when a susceptible person has that risk, that force of infection that they experience. And then after a while of being infected, an infected person might recover at rate gamma. So in the same way as we did before, we can say the average infectious period is 1 over gamma units of time, just the same as with the SIS equation. But the difference is we've now got this compartment for recovered people. Okay. So we've got 3 compartments. So we've got 3 coupled differential equations now. So we've got our susceptible equations. They look very similar. Now we've got our infected equations, and the gamma part of this, the recovery, moves into our recovered compartment. So we've got nothing going back into susceptibles. We've got infected people going into the recovered compartment. So what might that look like? Well, if we start here with a high number of susceptibles and an infected individual, we get an epidemic. So we get an initial increase in the number of infected as more susceptible people become infected. After a certain point, we reach a point where it's difficult for an infectious person to find the susceptible person to infect. The chance of coming across them reduces because we're reducing the size of the susceptible population. And everyone who is infected enters the recovered class. So, we've got our initial epidemic, it dies out, and then we reach this point. And because we've got no replenishment, nothing going back into the susceptible class, this is where we stay for this example. Okay. So for diseases where we've got lifelong immunity and models where we're ignoring births or any sort of population movement, this might capture the dynamics that you're interested in. If you wanted to model something like measles, where you've got really long-term immunity, and you only wanted to model it for a short time frame, this might be appropriate. We'll come back to adding births and deaths and how they might affect things in the next lecture. Okay. So, here, because everyone who becomes infected eventually ends up in the recovered class, this final value of the number of recovered people captures everyone who ever was infected. So the only way that people go through this is they're susceptible, they get infected, and then everyone who's infected recovers. So this final value, R at infinity, we could call the final epidemic size. So that's the final proportion of the population that became infected. It's not necessarily everyone. So we wouldn't necessarily assume that everyone gets infected, because at a certain point, the chance of coming across this infectious person in the population is low enough that infections no longer start to happen. This is where the epidemic naturally dies out. So even though we're not thinking about things like births and deaths and other complexities, we still might have the case that not everyone in this model gets infected. Okay. And we'll come back to this turning point later. Okay. So, we've got an SIR model. There's a couple of key points. The disease reaches a point where the chance of an infected person coming into contact with a susceptible person is low enough that the disease naturally dies out. So we reach an epidemic peak, and then we've got a decline in the number of infections. And you can see this curve in a lot of epidemics. We've got initial exponential growth, it slows, we reach our peak, and then we've got a slow exponential decline in the number of infected people. And it's the case that not necessarily all individuals become infected. So, obviously, depending on the disease and the time frame that you're interested in, this SIR model can capture an awful lot of dynamics. It's got a lot of assumptions, and we'll come back to those, but it can capture some dynamics pretty well. Okay. So we might be interested in, well, when does this point occur? Why have we got an epidemic peak, and why do we not end up with everyone getting infected? And for that, it's useful to think about an epidemiological quantity that we use quite a lot for talking about epidemic turnover, we might say. So what's the point at which we're no longer seeing a growth in infections? So we're going to define something called the basic reproduction number, R0. You've probably seen this tons. It used to be that nobody had looked at R0, but obviously recent events. When we're thinking about R0, we're thinking about the expected number of secondary infections produced by one infected individual in a wholly susceptible population. So if you imagine right at a beginning of an outbreak, we've got one infected individual, everyone's susceptible, what is the potential of that one infected individual to infect others? That's what R0 is giving us. There's something else that goes into this, and it's over their infectious period. So before that one infected individual recovers, how many more people are they going to infect if everyone's susceptible? It's nice because it gives us a threshold. So if R0 is greater than 1, if that one person goes on to infect more than one person in the next generation, we'd say, then you can see that the epidemic is growing. We've gone from 1 to 2. Each of those has got the potential to infect 2 more. You can see it's growing. If that one person doesn't manage to infect another person, maybe they infect 0.5 of a person, then the next generation, it's getting smaller. So we're not saying that the disease instantly dies out. It's because we're thinking about these generations. So in the first generation, if this is greater than 1, maybe we get 2 more infections. On that, it's 4 more infections. It's going to grow. On the flip side, if we're getting less than 1, in the next generation, we've got a smaller population of infected people. So eventually, if it gets smaller and smaller and smaller, it's going to naturally die out based on this threshold. So it's essentially a threshold between an epidemic and no epidemic, but it doesn't mean that the number of infections instantly stops. It means that we're going to die out over each of the subsequent generations. Okay. So it's the expected number of secondary infections given one infected individual. Here we're talking about the average infected person. So on average, and this is where it gets a little bit weird, on average, we've got one infected person. We're thinking about who are they going to infect before they recover. So we know that on average, they will be infectious for 1 over gamma. This is their average duration of time in the infected class. That's our kind of average infectious period. Here, we're going to define beta as the number of effective contacts. Maybe it's the number of efficient transmission events that they can do per time. So if you think about, okay, average infectious period, let's say, if I want to do maths in my head, let's say someone is on average infectious for 10 days, and the number of effective contacts per day is 0.2. So each day, their chance of having an effective transmission event is 0.2. So if we times 0.2 times 10 days, that will give us an R0 of 2. So we're thinking about how many infections is this person going to cause before they recover. So we can use this to define as our R0. So we're starting with our infected person. We're thinking about their effective contacts before they recover, and it might go on to infect 2 more people. So here, for this model, we would say that this is our basic reproduction number. Okay. We're going to keep coming back to how you work out the basic reproduction number and what it means. So this is the first time you see it, but we're going to do it at least in 2 or 3 other lectures in different ways, just because it's quite handy. Okay. So we're thinking infectious per generation. We've ended up with our R0. So the number of infections before that person recovers, given that everyone is susceptible. This is handy because we can use it in our model equations. So we have exactly the same equations before, but everywhere we've got beta over gamma, we've put in R0. So now we've directly used it in our equations. And there's a tiny bit of rearranging, but you can see now we've got R0 in our equation for I. We know that if we've got something like this, where we've got a curve and it reaches a maximum and then starts declining, that at this maximum, our derivative of 0. That's our local maximum. So at this point, the I by dt is 0, so we're changing our gradient here is flat. Okay. That happens if we set this equation to 0 and rearrange. That happens when the proportion of susceptible people is equal to 1 over R0, just from rearranging this equation. Okay. So we've got a nice threshold for epidemic growth. We've also got some information about when our epidemic is going to turn over, when we're going to stop growing, and when we're going to start declining in terms of the number of infected people. And just a note, R0 is something very different to compartment R, just to be careful. Okay. So, we can start thinking about useful ways to estimate R0. Sorry, go on.
So for the SI model, we do not have the basic reproduction number for the SI model forecast.
SI model. Ooh, that's a good question. Yeah, because the infectious period for that, because once you get infected, you just stay infected. So the infectious period is the rest of your life. So it gets a bit weird there. We'd mostly focus on beta for that model. Not actually come up with before. But for the SIS model, we do.
You can define an R0 using what Katie's about to tell you about. So using the exponential rate of growth.
Yeah.
Yeah, it's a trick that's sometimes used for network models as well, where, yeah, the concept of R0 is a bit, it means different things depending on the question you're asking. And sometimes if we were to compare between models, we look at the rate of exponential growth. So we can define an R0, which is for an SI type model, which has a similar interpretation based on the rate of exponential growth that we see. But effectively, R0 is always greater than 1 in the SI model, as long as you've got
Yeah.
more than 0 infected. So it's not such a useful concept.
Yeah.
For the definition of the reproduction number, would I be correct if I say it's the expected number of cases of secondary infection produced by an index case?
Yes. So, yeah, index case in that we're thinking about that infection in a totally susceptible population. So it might be the index case in that population. Yeah.
And is this applicable in all setup, like in new emerging disease, seasonal outbreaks, and endemic diseases?
Yes. It gets fun when you start thinking about R0 in terms of seasonality or the effective reproduction number in seasonality. Maybe that's a whole different lecture. We don't actually have that. If you want to talk about that, happy to. But yes, this concept's certainly we're going to go through a few different examples where you're still calculating R0, but it means quite different things. So tomorrow we'll go through an example with cholera in terms of R0, just to show how to calculate it for different model structures as well. But yeah. Okay, where did I get
So I
to?
think your definition was fine.
Yeah.
But the extra words of emphasizing it's a single infectious individual is important. That's implied by the index, but not essential. But the missing bit is a fully susceptible population.
Yeah.
If you've got any reduction in immunity in the population, it becomes an effective reproduction ratio, which is still useful, but it's not R naught.
Cool. Okay. So we can think about estimating R naught by thinking about what does our dynamic behavior look like at the beginning of an epidemic. So at the beginning of an epidemic, we're saying that everyone is in the susceptible class, everyone's susceptible. And here we've set our population size to 1, just to be frustrating. And we can think about what does our equation for our infected class look like at that point. So we can rearrange this, our equation. We can take into account that the S class is everyone, it's our total population. And that means that we can rearrange this like so. So we've got beta minus gamma times I. So this is just a constant. So this looks like exponential growth, right? So we've got a constant times the population in our differential equation. We can do that by substituting in the value or the equation for R naught. So R naught in this model is beta over gamma. So we can rearrange this slightly to include beta over gamma. And now we've got an equation for, at the beginning of an outbreak, exponential growth of our number of infected people in terms of R naught. So if you had time series data where you've got a number of infections occurring per day and it looks like it's growing exponentially, you can use that to start getting an idea of what R naught is in that setting. Because this is a differential equation for exponential growth, we know we can solve it. We've solved things that look a bit like this before. And we arrive at this. So our initial number of infected individuals, and then e to the gamma R naught minus 1. Okay. So we've solved our I class. We're thinking about the beginning of an epidemic, everyone's susceptible, and then we can use that to get an idea of R naught given we've got appropriate data on that stage. So we might have a couple of questions around this. So what are the units of R naught and what factors not included in this model might affect the estimates of R naught? There's loads. So firstly, units of R naught, no units. If we think about it, it's beta over gamma. Both of these are rates, so the units cancel. So we've got no units. What factors might affect our estimates? We could keep going on this. First one being underreporting, especially at the beginning of an outbreak, especially if surveillance is not used to looking for that particular pathogen in that environment. So underreporting is an issue, lagged reporting, that kind of thing. We might have variable case definition. So what is categorized as a case? Are we talking all infections, or are we talking only people with severe disease? And we're waiting for those to reach healthcare or something else. Population might affect this. Lots of things might affect this. Okay. We will keep coming back to this though. So, summary on this lecture. We started on compartmental modeling. We know it's a continuous process, but we split it into compartments that we're really interested in. We talked a bit on mass action mixing, well-mixed populations, frequency-dependent contact. And we looked at what some of those rates mean. So we're thinking if we've got a constant rate, we've got an exponentially distributed waiting time. So we've got a decline in the number infected at the time. And we've looked at basic reproduction number for the first time, but as I said, we're going to keep coming back to that in other lectures. Okay. So, whoa, we are tight on time. We've got another lecture on SIR models. Does everyone want 2 minutes break to just stand up and like have a moment? And then we'll start and try and get done by the coffee break. Oh, 1 second, I'll come to you. Was that?
I heckled a lot there. Sorry. Lectures are very good.
Okay, hopefully everyone's had a chance to at least stand up, get some fresh air, move around a bit. We're going to hopefully answer some of the questions that have been coming up. So obviously the models that we've shown so far, they've got some implicit assumptions, but they're also missing some key things that you might think about including in an epi model. So the objectives of this lecture are going to start looking at some of those key assumptions. So we might be interested in including births and deaths in our model. We might want to include aging. If we include age, we can start looking at age-dependent contact. We can start thinking about age-dependent interventions. Let's say we're vaccinating infants. If we want to model vaccinating infants, we need age in our model. So we've got some implicit assumptions. We've already started looking at what they might be. Sometimes they're fine. Sometimes those assumptions are okay in the question or the disease or the context that we're looking at. But sometimes they're going to affect the dynamics that we're trying to model in ways that we don't want them to. So we're going to look at some of those assumptions, include talking about age structure, and then start thinking about how we calculate R0 in an age-structured population. Okay. So, we haven't got to the practical yet. In your practical that is coming up tomorrow, you're going to start simulating an SIR model. You're going to explore epidemic peak, how long an epidemic lasts, what the parameters mean in terms of that peak number of infections, and how long that epidemic lasts in your practical tomorrow. I'm going to skip that slide so you can explore it on your own and have a look at it. So, we've got this familiar sort of figure. Here we've got our number of susceptible people declining as they get infected. We've got our epidemic, our outbreak of a disease or infection. So we get initial exponential growth in our number of infected people till we reach this threshold, this turning point, where we're getting S over N equal to 1 over R0, that threshold we defined before. At that point, our number of infections starts declining and our outbreak dies out. Okay. So if we've got an SIR model and we don't have any way that the susceptible population is replenished, we just end up here, right? We have our epidemic, great, we've got a peak, it dies out. You'll be simulating this tomorrow. You can see how it's affected by different parameters, and we end up over here. And this is where we're going to stay in this particular model. Okay. So, what happens if this is not a very good representation of your particular question, your particular data that you're interested in? So it might be that you're simulating more than one epidemic. You might have an endemic disease. You might be seeing oscillations every few years, like the lynx population. One of the things that you might like to include if you're thinking over a longer time period is including births and deaths in your model. So here essentially we've got our SIR components and we're adding a few extra arrows. So here we're assuming all births are susceptible. It's an assumption. There we go. We've made the assumption that everyone born is going to be susceptible. Obviously, there's some diseases where that's not the case. We're not thinking about maternal antibodies. We're just going to assume everyone born is susceptible. And then each compartment, we might see deaths. So at the moment, we're going to think about just per capita death rate. we're not necessarily thinking about disease-related mortality, but you can start to see how you might include that as well. Okay, so we've got our SIR model and we're adding births and deaths. What happens then? So we've simulated our initial epidemic here. Our susceptible population has declined, but now we've got births to replenish that susceptible population. And we're assuming that people, when they're born, go into that susceptible class. So that number of, or proportion of susceptible people starts growing. Also, people can die. So the recovered class, the number of people in there, starts declining just through per capita mortality. If this proportion of people susceptible grows enough, it means that we've got enough people to fuel another epidemic. Because we always need susceptible people to exist before we can start infecting them. So we need to reach a threshold where there's enough people in the population who are susceptible to fuel another epidemic. Note here, we're not having anything like stochastic die-out. That's another lecture that's coming up. Okay. So the time period that this takes might be affected by how quickly people are born and how quickly people die in a population. But essentially, if we've got an SIR model with births and deaths, this second epidemic or third epidemic can start to happen. Okay. So let's have a look at how the equations change. So now we're adding a couple of extra parameters. We've got a per capita birth rate and a per capita death rate. So we've got our SIR differential equations. We've got an extra term here, Bn. So n here is our total population. So everyone is either susceptible, infected, or recovered. And for each of our equations, we've got this mortality. So people in S, I, and R can leave the compartment if they die. So we've got our infection term, our recovered term. They both stay the same, but we've got these demographies, and just to remind you that the total population size is n. In this case, we're no longer necessarily dealing with a population size that stays the same. In the previous example, there was nothing that was going to change the population size. It was completely enclosed. But here, we've got people being born, and we've got people dying, and they might be at different rates. So the way we understand how our population size might be changing is by looking at these equations. So we know that everyone in the population is either susceptible, infected, or recovered. So if we look at the differential equation for the total population, that's going to be the sum of the three differential equations for S, I, and R. If we add them up, a lot of the terms cancel. So all of the infection terms cancel, recovery terms cancel, and we end up for our total population size with a differential equation that looks a bit like this. So dn by dt is equal to b minus m times m. So you can see, if the birth rate is equal to the death rate, this goes to 0. We've got a constant population size. If our birth rate is greater than our death rate, we've got a growing population. If mortality is greater, then we've got a declining population. Okay. But with this setup, we no longer necessarily have a constant population size, unless this is true. Okay. So we've got our equations. We can start thinking about how they correspond to key parts of our epidemic sort of timeline. So we've got our first outbreak. We reach this peak. That's where S over n is equal to 1 over R naught. But now we've got a slightly different equation for R naught. We'll come back to that. So if we think about going along this timeline, initially we've got exponential growth. We've got an initial increase in infected people. We reach that peak. We start to decline. And we have to wait until our susceptible population is replenished so we can fuel another epidemic. Again, if we're thinking about R naught for this model, we're still thinking about the same idea. We're thinking about the secondary infections given one infectious individual in a totally susceptible population over their infectious period. What's different is the infectious period here. So we've still got this beta as kind of our effective context, but people in the infected class can exit that compartment by either recovering, like the previous model, or by dying. So our average time in the infected class is now dependent on both gamma and our mortality rates.
Please,
Yeah?
why do you have the IDT greater than 0?
Oh, that's just at this point. So at this point, we've got di/dt greater than 0, which means we've got a growing epidemic. Here, we've got to the point where di/dt is 0. So that's our peak. And then we start declining, so it's less than 0. So this is just going through the different steps on the outbreak. Yeah, so here we go. di/dt is at our peak, gradient 0. We set our equation 0. This is the turning point of our epidemic. As I mentioned, our R0 now depends on gamma and mortality rate because these are the two ways that someone might exit the infected class. So at this point, where we've got that turning point, we've got a new kind of threshold, but it's still R0. That's how we define R0. Okay. Then we can start stepping through. So here we've got the decline. So the rate of di/dt is now negative. We've got decline in the number of infections. That's because there's not enough fuel for our outbreak, not enough susceptible people, until a certain point here, where we get a number of susceptible sufficient that we can start growing that outbreak. So you can see, really this is where we see our epidemic, but it starts earlier on. We have to wait for that population of susceptible people to be replenished. So, going back to this, we've now got the situation where we can have an epidemic and then our susceptible population becomes replenished. If we look further on and we keep extending this time series, and yeah, this is the point where the number of infected starts increasing again because we've got enough susceptibles. If we extend this time series longer and longer, we can see that, like with some of the other examples, we get some oscillations. We get our initial epidemic. It's quite steep. Our number of infections decreases. But then we've got enough susceptible to get another epidemic or outbreak. And we oscillate until we reach an equilibrium point. So an equilibrium point because we're at a steady state. Okay. So for this, we've got an endemic disease, which means that we've got a small proportion of the population that's always infected at steady state. Okay. You can only get this, well, you can get this if we've got some replenishment of the susceptible population. So either through births or deaths or going back to that SIS model. If we looked at that in a phase diagram, we'd have something like this. So here, along the bottom, we've got the proportion of susceptible people. Here, we've got the proportion infected. If we start with lots of susceptible people and a small number infected, that susceptible population gets smaller as they become infected. Our number of infections grows until we reach a threshold point. We've seen a lot of phase diagrams today. So we essentially swirl around to our endemic equilibrium in the same way that we've looked at other dynamics like this. Okay. So what is that steady state? What is the equilibrium? Well, we know that we get to the equilibrium by asking the question, what happens when our differential equations are equal to 0? So if we split all of these compartments up, for the S class, we've got births, infection and deaths affecting it. And let's say for now we've got a balance between births, which is replenishing our susceptible population, and infection and deaths, because that way we'll have the change in the susceptible population equal to 0. So again, we're always thinking about what happens if our differential equations are equal to 0. So we can do this for each of our equations and think about what we need to balance with these. And we might be doing this so we get the answer to the question, what number of infections do we expect to see at steady state? If we got an endemic disease, how many people are we going to expect to see infected every year? Maybe that's going to affect how we provide healthcare or think about timing of interventions. So we set the I by dt equal to 0. We rearrange our equation. These little stars are just to denote these are the values of our variables at equilibrium. That's all the star denotes. If we set this equal to 0, we can rearrange and we get our equilibrium value of proportion of susceptible people is equal to 1 over R0. Okay. Once we have that, we can start solving for the other equations. Use the fact that everyone is either susceptible, infected, or recovered to finally solve our entire set of equations at equilibrium. So again, the little stars are to denote that these variables at equilibrium. So this gives us our answer. Given our particular model structure, this is the proportion of the population that we expect to be infected at endemic equilibrium. Okay. So we've got oscillations going towards a steady state. This is our equilibrium point. You can see this in some time series, although visually that's hard to see. Now you've got the slides, you can see that in a bit more detail on the slides and have a look. But these oscillations heading towards an endemic steady state are things that we observe for real diseases. Okay. So, to do this modelling and to set the equations up as we have, we've made some explicit assumptions, like everyone born is born susceptible. And we've made some implicit assumptions, like we've got a constant rate of recovery. Some of those make, well, a difference to the dynamics that we might be modelling, and some might be okay for our particular problem. It's good to know what we're assuming, so you can decide if it's important for your context, your question. Let's go through some of the assumptions. So firstly, mortality. We might have differing assumptions around mortality per age group, and that might affect things like what we might expect to see in the age structure of the population. So if we look at these age kind of population pyramids, you can see that the shape of them differs between these different populations and these different times. This might be important to capture in your model. So if we think about mortality, here we're just looking at how our population dies, how that mortality affects our population. If we had no births at all, we'd see exponential decline or decay. And again, we've got a constant risk m of death at each time step. We've seen this differential equation before. We know we can solve it, integrating to get an equation that looks a bit like this. This is just like what we did with the recovery rate. So, what does this look like? Well, at the beginning, if we start with everyone alive, over time they've got a risk of dying. Because it's exponential decay, initially this is quite a steep decline, and then over time it levels off. Okay. You can see that this is going to give us a proportion in each age group. And okay, up to the age of 100, that might be good for your population, but we've still got people living to the age 200 and above. So you might want to think about how worried you are about that in your particular model. If we think about the time scale that we might be interested in looking at, let's say we're thinking about something like flu, where you're infected for a few days, then maybe you're not too worried what this mortality or this like timescale is going to look like, because really all of the dynamics that you're modeling happen in a few days. It's not going to be affected by the mortality. If you've got something else, maybe where people are infectious for the rest of their life, then what you assume about that lifespan is quite important. That's going to affect your dynamics. So depending on your context, you may or may not be worried about this assumption. We can do the same thing with recovery. We do what we did before, so we know that we can solve this and look at the average infectious period. Again, if we start with everyone infectious, there's a steep decline. There's a lot of people who recover pretty fast. But there are some over here that are infected for a really long time. This has got implications for the dynamics you're going to see coming out of your model. They may or may not affect how well it behaves in terms of the context you're interested in. In reality, for a lot of diseases, we might have something more like this, where a lot of people are infectious for a certain number of days. A lot of people are infectious for maybe 3 days. A few people recover a little bit faster. A few people recover a little bit slower, but nobody's staying infectious for days or weeks or months for this particular thing. So you might want something a bit more like this in terms of your infectious period. Okay. Then we've got the risk of infection. So we've got this, our force of infection. We've defined it before. This is one of the things where you might look first for when you want to add complexity to your model to capture different contexts or different questions. Here we've got different diseases, pertussis and tuberculosis, and looking at, okay, what is the number of, or density of infections per different age groups in pertussis? This is pre-vaccine, this is post-vaccine. These are very different in terms of the number of people in each age group that's getting this disease. So clearly something is happening here with their risk of infection going on. Okay. So we've got some assumptions. We might be very worried about them, depending on the particular question. We might not. It's good to know what they are to make sure that we've decided whether we're worried or not. So we've got a few assumptions. If we had a small population, one individual, the risk of the disease dying out just by chance is quite high, so maybe we want to think about a stochastic model. You'll go on to that later. We might be interested in the case where that lifespan of an individual affects how long they're infected for. So for example, if we had a model looking at mosquitoes and people, a mosquito gets infected and then remains infected for the rest of their life, what we assume about their death rate is very important because that affects their infectious period. We might be looking at the early stages of an epidemic, we might be thinking about differences by age, and we might also be wanting to model things targeting particular parts of the population. All of this means that it's worth considering the assumptions and maybe adding slightly more complexity to our model to capture them. So what can we do about them? We can do things like look at different distributions, so going back to the recovery rate, and for the age-dependent stuff, we can add age into the modelling. So, exploring different distributions. So you're going to look at this a bit. If we're thinking about our infectious period, and you know I had the exponential decline in the number of infected people, and then we had that gamma distribution, so that peak number of infected people staying infected for about 3 days and then some people either side. We can approximate that before jumping into different ways of modelling just by adding multiple infectious states. So what does this do? Well, it means that if rather than having someone susceptible who gets infected and then recovers, we've got this. So before someone infected recovers, they have to stay infected for a bit longer. So we get round the idea that some people are going to recover really fast just by adding this simple addition to the model. Okay. So what does this do? Well, as we add more and more compartments like this to the model, it gets closer and closer to approximating this dotted line here. So this is the gamma distribution. So again, we're forcing the model to keep people infected for a certain duration, and then they can recover exponentially from that. If we add enough compartments, this gets closer and closer to a gamma distribution. Again, you need to decide for your question whether this is worth doing, whether it's going to add benefit to your model. Okay. If we think about including age in our model, we might want to consider age, and really we know that everyone ages continuously, so unfortunately as time is continuous, so is age. It's a depressing thought. So we might want to include it explicitly like this. This now means that we've got our S compartment as a function of age and time. And I know we said we were only going to look at ordinary differential equations. This is the only time that we look at partial differential equations except tomorrow. So here now we've got partial derivatives. The susceptible population is a function of age and time. So we end up with something like this. Age is modeled as a continuous process. We know it is. And then we can do all sorts with this. We can specify things like age-dependent transmission, all sorts of continuous processes. Problem is, partial differential equations are really a pain to work with. So is it worth adding this complexity? Are there other ways that we can do it? Especially as if we collect information on people and we're asking them their age, you don't normally say 21 and 3 months and 7 days and 2 minutes, you just say 21. Okay. So is it worth adding? Well, we could consider approximating it. So here we might have our SIR model, but we've now included something like annual age groups. So we've got our age 0 people, that's where all the births happen. Again, we're assuming everyone's born susceptible. And then we've got an SIR model for each age group. This gives us tons of flexibility. We can still do age-dependent transmission, recovery, maybe a risk of severe disease varies by age. We can do a lot of things with this. We're still working with ordinary differential equations. We've got lots of them, but we're now probably not working with them by hand anyway. We're probably simulating them. So we can do a lot with this kind of framework. Okay. If we've got that structure, we can start getting slightly more complicated with our mortality. We can do things like this, where you assume that everyone dies at the age of 69. I'm not sure when you'd want to do this, but you could. We can keep our exponentially distributed lifespan. If this is a good approximation of the age pyramid for our population, maybe we keep it. Or we could do something like this. So the Gompertz distribution is a nice one for having a risk of mortality that varies with age. So we can start building in complexity because we've got that age structure. Okay. And lots of other options as well. We might want to, in the same way that we looked at different distributions for mortality, we might want to go back and rather than approximating the gamma distribution for the infectious period, we might want it explicitly. It's got a few parameters. So either we want to set those up, maybe we're reading from the literature and find something appropriate for our disease area. Maybe this is something that we're estimating from our data sets. But we can start thinking about including this distribution explicitly. Again, it's adding complexity. You've got to decide if it's worth it. Okay. And then finally, if we've got this age structure, we can start thinking about getting more specific with our transmission, our force of infection. So we now can have our lambda as a function of A. So, got a few options for this. One, maybe we've got a constant lambda. It's quite boring, we've seen that. I won't spend time with it. One where maybe your force of infection only depends on people in the same age group as you. This might be appropriate for some model structures, maybe if we're not thinking about age, but some other sort of structure. But essentially, you're only infected by people in the same age group. Okay. And then we might have this. So here we're saying that the force of infection by age depends on other age groups as well. But we might have different transmission rates between different age groups. This gives us like the maximum amount of flexibility. Again, with a lot of flexibility means we have to maybe either make some assumptions or have a lot of data to inform it. If we've got a matrix like this, so this is giving our transmission rate between age 1 to age 1 or age 2 to age 1 and so on. We've got a lot of flexibility here. We've also got a lot of parameters. So either we want to make some assumptions or we want to estimate those. We could have something like this, and again, you'll be exploring this in the practical. So here's the special case where people only mix or get infected by people in the same age group. Everything's 0 except the diagonal. Okay. We might have this case where you're only infected by people in other age groups, never your own. So we've got the off diagonal. You might see this for other structures more commonly. Or you might want to use some estimates of contact between different people in the population to inform your model. So for example, these are a couple of studies looking at the number of contacts between one age group and another age group. So here, the brightness of the colour indicates more contacts. You can see we've got different mixing patterns for these different populations. This is a whole thing on its own. You might have seen some of this when modelling COVID, because people's contacts changed. And they changed over time and with different interventions. So this matrix, this picture, changed quite a lot. So you can see, this is one example where they were looking at, this is the polymod matrix. So this is the same thing, just not as granular, pre-COVID, and then with social distancing interventions in place. So our contact structure changed, and that meant that the estimates of key parameters in our models, depending on this contact structure, also changed. Okay. So, final thing is, okay, we've got this model, we've added age structure, now we've got hundreds of equations, but that's fine, we'll simulate them just as long as we make sure that we've not made any mistakes in the coding. Final step is, we've got a structured model. How do we calculate R naught? Our definition of an average infectious individual captures both, age group 0 to age group 50. So now we need to think about how do we include that structure in our R naught. What we do is we use the next generation matrix. We're going to go through this in far more detail tomorrow. We're going to step through how this comes about. But essentially, we're thinking rather than one infectious individual infecting another, we've got an infectious individual possibly infecting someone in the same age group or infecting someone in another age group. So let's say we've got a model where we're modelling children and adults, so only 2 age groups. So we've got a risk that a child infects another child. We could say that's 2. This is our potential reproduction number from a child to a child in one generation. We're going to say that reproduction number from a child to an adult is lower, 0.5 maybe. They've got different sort of contact. And then we've got these reproduction number from an adult to a child. It's a bit different. And again, to an adult to an adult. Maybe adults are working together, they've got a slightly higher chance of coming into contact. Maybe children are in school together. So we've got a structure to our potential reproduction of this epidemic, depending if we're talking about children or adults. Our R0 definition is still talking about the average infectious person. So we're sort of averaging between a child and an adult here. So if we do this, let's say we start with an infection in children, we maybe get 2 more infected children, half an infected adult. If we start with an adult, we get these splits of children and adult. In our first generation, we end up with 4 more infections if we add this all up, starting with 2 infectious individuals. So on average, our reproduction number here is 2. If we then propagate that onwards, so this child then goes and infects another child, and we keep doing that, we keep looking generation to generation, we work out the next generation, and we get an average number of new infections per infectious person, it's being 2.06. We do it again, 2.098. So it looks like, on average, the infected person produces around 2 secondary cases per generation. This is a very approximate way of doing it. It's just making you think about, okay, per generation, on average, how many new infections are we going to see? As I said, we're going to go through the next generation matrix in detail tomorrow, so you can see where it comes from and how we use it. Okay. So, we've had our SIR model. We included births and deaths. We now can have endemic infections, but we need to start being careful in terms of some of our assumptions, particularly ones about demographic timescales, how they interact with the epidemic timescale. We might want to add complexity to our model through including age structure, and if we do that, we can change the sort of distributions that we've got in our model. It does mean it's a bit more complex to work with, and it changes how we estimate R0 or calculate R0, but we'll go through that in a bit more detail tomorrow. Okay. So, I think we've got a coffee break now. If you've got any questions, please ask me, but I think everyone should have a coffee and move around. It's been a lot of SIR models. So, happy to answer any questions, but definitely get a coffee.